Hello, my name is Israel Palacios. My group members are Cody Skipper and Cristal Miller. Our material is titanium dioxide. Titanium dioxide is one of the many materials that can be electrospun in order to create solar cells. It is a compound that is comprised of titanium-4 and oxygen atoms, which are ionically bonded. One titanium atom is bonded with 6 oxygen atoms. It usually has a tetragonal unit cell structure. Considering its composition, it has a similar valence electron structure to that of oxygen, which means that its furthest electrons are in the p shell. It naturally occurs in 3 different crystalline structures: rutile, brookite, and anatase. The anatase structure is the most important when looking at photoelectric cells and conductivity. In the anatase structure, it is amorphous, which helps with conductivity. This means that electrons can move freely throughout the material due to the uneven distribution of atoms. Its amorphous structure also helps with doping agents. It can be easily doped with different resins and composites in order to increase its conductivity. This is beneficial when considering solar cells. Its valence electron structure also helps with absorbing energy. The furthest electrons in the p shell can be easily knocked out of orbit. This allows for more excited states, which means that titanium dioxide can convert more energy from photons into usable power. This is beneficial when considering solar cells. As an electrospun material, it can absorb more energy than silicon and is less expensive than silicon is. Even though the fibers can be easily peeled off of the surface, it can be combined with different resins and composites in order to increase its adhesive property. This makes it a prime candidate for solar cells due to its configuration for conductivity and geometry that allows it to work with photons. The structure of titanium dioxide also leads to some interesting properties.
Thank you, Israel. Now that you've learned a little bit about the structure, I will tell you about the electrical, mechanical, and physical properties of titanium dioxide. I'll also tell you about the applications that those properties allow. Titanium dioxide has several interesting properties. One is the low absorption coefficient. Materials with a low absorption coefficient poorly absorb light, and it will appear transparent if the material is thin enough. Another interesting property of titanium dioxide is a high refractive index. This allows titanium dioxide to be used in high-performance photovoltaic cells that use semiconductors to convert sunlight into clean electrical power. The anatase titanium dioxide phase has semiconductor properties, allowing potential for several different applications. It is the more photoactive phase due to its low velocity. The low velocity recombination of photo-generated charges in its structure allows it to be used in sensors, optoelectronic devices, catalytic devices, and solar cells. The photo transport properties are related to the electronic band gap of the electrospun fibers. This is affected by particle size, shape, phase transitions, and surface charges. These properties make it ideal for use in dye-sensitive solar cells. Being able to control the band gap edge levels with respect to nanostructure and dyes allows the generation of voltage. Photocatalytic properties of a material allow oxidation of organic compounds with formation of only carbon dioxide and water. Since most of the pollutants are organic, titanium dioxide can decompose these under UV light and no toxic waste will be produced. It serves an important role in disinfection application, water, and air cleaning as well. It is preferred over other metal oxides with similar properties because it is abundant and non-toxic. The processing of titanium dioxide into electrospun fibers also adds to its capabilities. Now that I've talked about properties and applications, let's learn just how titanium dioxide is processed. Cristal is our processing expert, and she will cover the basics for you. Thank you.
In order to produce electrospun titanium dioxide fibers, we must begin by gathering the necessary materials. Before the electrospinning process can be started, the titanium needs to be mined. A common place for mining is the Sierra Rutile Mine, which is located in the country of Sierra Leone. After the material has been mined, it must be put through a purification process to produce a pure form of titanium dioxide. The purification process can be accomplished two different ways. One of the possible processes is the sulfate process, but another option is the chloride process. The sulfate process starts with an iron titanium oxide material that is treated with sulfuric acid. Once the material is treated, the titanium oxide sulfate is taken out of the mixture and converted into titanium dioxide. The chloride process requires a rare material that must contain at least 70% rutile. This is then reduced using a procedure that requires carbon, and then it is oxidized with chlorine. This method produces a liquid that must be distilled and converted into titanium dioxide. The chloride process is preferred over the sulfate process due to the financial and environmental aspects of the procedures. Once the material is purified, the process of electrospinning can begin. The titanium dioxide is spun by mixing a solution composed of PVP, acetic acid, and TTIP with the purified material. The mixture will sit overnight to increase the surface area of the fibers. The mixture will then be put into a syringe and a voltage will be applied to the syringe. The voltage will create a stream of fiber that will be propelled onto a conductive glass surface. This process results in the formation of titanium dioxide electrospun fibers. After the electrospun fibers are formed, the manufacturing process can begin. This specific material will be used in solar cells. The application for the material requires excellent photocatalytic properties. To ensure the best photocatalytic properties are reached, a mixture of anatase and rutile will be used. This mixture should be a 4:1 ratio. The final product is a fine white powder that has hydrophilic characteristics. These characteristics allow the material to interact and bond more efficiently with the water molecules. The surface of the material is coated with hydroxyl groups that form bonds with the hydrogen molecules in the water. Combining all of these steps result in a usable product that can be utilized in making solar cells.